If the entire solar system from the Sun to Neptune were shrunk to the size of a coin, the Kuiper Belt would stretch the length of a football field. Everyone thinks they know what the solar system looks like, but that diagram, the one you've seen 1,000 times, is one of the most misleading images in the history of science. The Kuiper Belt, a colossal, mysterious, frozen territory, crushed into near-nothingness on every poster ever made, is actually the dominant structure of the entire outer solar system. Now, let's find out. There is an image almost every person alive has seen. It hangs on classroom walls across the country, printed in textbooks from elementary school through high school, embedded in science documentaries, reproduced on the covers of magazines, rendered in animations on educational websites. The solar system, the sun glowing on one side, 8 planets stretching outward in a neat line, each one labeled, each one sitting at what appears to be a reasonable distance from the next. Mercury close in, small and gray. Venus just behind it, slightly larger. Earth with its familiar blue tint, the one planet that feels like home. Mars a little further out, rust-colored and thin-atmosphered. Then the gas giants Jupiter massive and banded with storms, Saturn ringed and elegant, Uranus tilted on its axis, Neptune a cold blue marble sitting at the far end of the line, and beyond Neptune, a thin strip, a modest band of icy debris, labeled the Kuiper Belt, drawn like a slightly thicker version of the asteroid belt that sits just past Mars. That image is comfortable. It is legible. It fits on a page, fits on a wall, fits inside the mind of a 10-year-old who is learning the names of the planets for the first time. It is the visual shorthand for everything humanity knows about its cosmic neighborhood, condensed into something a person can take in at a glance. It is also deeply, structurally, and almost insidiously wrong. Not wrong in the way a typo is wrong. A small error that slightly distorts an otherwise accurate picture. Wrong in the way a map of the United States would be wrong if it showed Los Angeles and New York separated by the same distance as 2 city blocks. The relationships are intact. The order is correct. Mercury really is closest to the Sun. Neptune really is farthest. The Kuiper Belt really does lie beyond Neptune. But the proportions have been so catastrophically compressed that the resulting image no longer resembles the thing it claims to represent. It resembles a convenient fiction, drawn with good intentions, reproduced with good intentions, and believed with complete sincerity by generation after generations of people who never had any reason to question it. The reason this compression exists is not carelessness. It is geometry, and it is brutal. To draw the solar system to true scale on a single piece of paper, showing both the sizes of the planets and the real distances between them accurately, the paper would need to be enormous in a way that makes the word enormous feel inadequate. If the sun were drawn the size of a period at the end of a sentence, Earth would be a speck invisible to the naked eye, located roughly 3 meters away from that period. Jupiter would be across the room. Neptune would be somewhere near the far wall of a very large building, and the Kuiper Belt, the structure that most diagrams represent as a thin strip just past Neptune, would extend well down the hallway beyond that wall, past 2 or 3 closed doors, before finally beginning to thin out. No textbook page can hold that. No poster fits on a classroom wall at that scale. No television screen, no tablet display, no standard monitor can render it without making the planet's invisible dots separated by vast stretches of empty pixels that communicate nothing useful to a viewer. So every diagram that has ever been printed makes the same silent, necessary compromise. It shrinks the distances. It pulls the planets closer together. It gives Neptune a position that looks, visually, like it is only modestly further than Saturn. And it draws the Kuiper Belt as a narrow strip, perhaps a centimeter or 2 wide at most, that appears to be a minor geographical afterthought, sitting politely at the edge of the picture. Easy to overlook, easy to underestimate, easy to file away as a small detail at the margin of something larger and more important. The compromise is understandable. The consequence is not. Because the human brain does not process diagrams the way it processes footnotes or disclaimers. When a person sees an image repeated hundreds or thousands of times throughout childhood, adolescence, and adult life, the brain does not file it under approximate illustration. Consult raw data for accuracy. It files it under "this is what reality looks like." The visual becomes the mental model. The mental model becomes the baseline assumption. And the baseline assumption, once set deep enough in the mind through years of repetition, resists correction even when the correction is standing right in front of it, written clearly in numbers that anyone can read. The result is that most people, including educated, scientifically literate people who follow space news and know the names of NASA missions, carry an unconscious assumption that the planets of the solar system are relatively close together, that the gap between Saturn and Neptune is a manageable stretch, the kind of distance that feels large but not incomprehensible, that the Kuiper Belt is a narrow ring, a modest collection of icy rocks sitting just past the last planet, the way a fence sits just past the edge of a yard, defining the property line without dominating the landscape. Have you ever noticed that Neptune doesn't look much farther from the Sun than Saturn does on those diagrams? That feeling has a cause. It was built into the picture not with malice, but with the quiet necessity of making something fit on a wall. And it has shaped the way an entire civilization thinks about the outer solar system for decades, without most people ever realizing the shaping was happening. Here is what that compression actually costs, expressed in the simplest terms possible. On a standard solar system diagram, if the distance from the Sun to Neptune is represented as 30 centimeters, roughly the length of a standard ruler, a distance that feels modest and manageable on a page, then the Kuiper Belt, drawn to accurate scale relative to that 30 centimeters, would need to extend an additional 20 centimeters beyond Neptune's position, not 2 centimeters, not 5, 20 full centimeters of additional width, representing the classical region of the Kuiper Belt alone. The total diagram, from the Sun to the outer edge of the classical Kuiper Belt, would be 50 centimeters long. The Kuiper Belt itself would occupy 40% of that total length. It would not look like a thin strip at the edge. It would look like a major territory, a vast, sprawling zone that fundamentally changes the visual balance of the entire diagram. That makes the planetary region Mercury through Neptune look like a compact cluster at one end of something much, much larger. Instead, on almost every diagram ever printed, the Kuiper Belt is drawn a few millimeters thick, sometimes less, a sliver, a suggestion of a structure, a visual footnote pressed up against the right margin of the picture, easy to glance past, easy to mentally categorize as a minor detail, easy to forget entirely by the time the eye has moved on to something else. And so an entire structure, one of the most physically significant regions of the solar system, a zone that rivals the entire planetary system in scale, has been systematically absent from the public imagination, not through any deliberate deception, but through the innocent, practical tyranny of paper size and screen dimensions. The poster was never trying to mislead. It simply could not tell the full truth and still fit on the wall. The mental picture that resulted from a century of compressed diagrams is one of the most consequential quiet distortions in science communication. It did not change any facts. It did not alter any data. It simply made one of the largest structures in the solar system invisible by making it look small. And it made that invisibility feel like knowledge. But the numbers on paper still cannot show the thing that is truly staggering. What do those real distances actually mean? Before the Kuiper Belt can mean anything, distance itself has to mean something. And distance, at solar system scales, is almost pathologically resistant to human intuition. The numbers exist. They can be written down, read aloud, even memorized. But feeling them, understanding them, the way a body understands the distance between two familiar places, is something else entirely. It requires translation into terms that the human mind was actually built to process. Start with one number, 150 million kilometers. That is the average distance from Earth to the Sun. Astronomers encounter this number so frequently, use it as a reference point so constantly, that they gave it a proper name, the astronomical unit, abbreviated AU. It is the baseline measurement of the entire solar system. Every other distance of significance is expressed as a multiple of it. Jupiter orbits at 5.2 astronomical units from the Sun, Saturn at 9.5, Uranus at 19.2, Neptune at 30. The Kuiper Belt begins at 30 astronomical units, and its classical region extends to 50. The astronomical unit is the yardstick, and everything in the outer solar system is measured in dozens of them. 1 astronomical unit, 150 million kilometers. It sounds enormous in the abstract. It is almost impossible to feel in any meaningful, visceral way without a comparison that anchors it to lived experience. So consider this. Imagine getting into a car and driving at 60 miles per hour, a normal highway speed. The kind of pace that feels fast on a road, but routine on an interstate. No stopping for fuel, no sleeping, no slowing for weather or traffic or anything else. Just driving. Hour after hour, day after day, pointed directly at the sun. That journey, one single astronomical unit of distance, covered at 60 miles per hour without a single break, would take 177 years. Not days, not weeks, not even a few decades. 177 years of continuous driving just to cover the distance between Earth and the Sun, the shortest major distance in the solar system, the baseline unit against which everything else is measured. Light covers that same distance in 8 minutes and 20 seconds. That gap between what light can do and what any vehicle moving at any speed a human being can intuitively grasp can do is the first essential thing to hold in mind when thinking about the outer solar system. Because the Kuiper Belt is not 1 astronomical unit away. It is not 5. It begins at 30, and it ends at 50. Neptune sits at 30 astronomical units, 30 times 150 million kilometers. In raw numbers, that's approximately 4.5 billion kilometers from the Sun. Driving non-stop at 60 miles per hour, it would take over 5,300 years to reach it. The Egyptian pyramids at Giza were constructed roughly 4,600 years ago. A car that departed Earth the day the first stone was placed at Giza would still have centuries of driving remaining before it arrived at Neptune's orbit. Even light, traveling at nearly 300,000 kilometers per second, the fastest speed that physics permits anything to move, takes more than 4 hours to make that journey. When astronomers observe Neptune through a telescope on any given night, they are not seeing Neptune as it currently exists. They are seeing Neptune as it was 4 hours and 10 minutes ago, because that is precisely how long it took for the light reflected off its surface to travel across 30 astronomical units of empty space and reach the telescope's mirror. Voyager 2, launched in 1977, flung outward by carefully calculated gravity, assists from Jupiter and Saturn that added enormous velocity to its trajectory, took 12 full years to reach Neptune, 12 years of continuous flight, covering billions of kilometers, before the spacecraft finally passed through the Neptune system in 1989, and humanity saw that distant world up close for the first and, so far, only time. If you traveled from the Sun to Neptune, and the journey took 12 years by spacecraft, how long do you think it would take just to cross the Kuiper Belt? The Kuiper Belt begins exactly where Neptune's orbit ends at 30 astronomical units and its classical region. The most well-defined and densely populated zone extends outward to approximately 50 astronomical units. That is a width of 20 astronomical units, 20 times 150 million kilometers, 3 billion kilometers of width, measured only through the classical zone, before accounting for the scattered populations that extend even further. Hold that 20 astronomical unit figure next to something concrete. The distance from the Sun to Uranus, the seventh planet. The ice giant that precedes Neptune is 19.2 astronomical units. The width of the Kuiper Belt's classical region alone is greater than the entire distance from the Sun to Uranus. Every planet in the solar system: Mercury, Venus, Earth, Mars, Jupiter, Saturn. Uranus fits within 19.2 astronomical units of the Sun. The Kuiper Belt is wider than the span that contains all 7 of those worlds. Put it another way, if the solar system were a road, and someone had already driven from the Sun all the way out past every planet, to Uranus, 19.2 astronomical units of road, they would need to drive that entire distance again, plus a little more, just to cross the width of the Kuiper Belt, not to reach the Kuiper Belt, to cross it from its inner edge at Neptune's orbit to its outer classical boundary. New Horizons launched in January of 2006. The fastest object ever sent from Earth at the time of its departure traveled at approximately 36,000 miles per hour relative to Earth and received an additional velocity boost from a Jupiter gravity assist. Even at that speed, it required 9.5 years of continuous flight to reach Pluto, which orbits at roughly 39 astronomical units, a point that lies inside the Kuiper Belt, not at its outer edge. The outer boundary of the classical belt sits 11 astronomical units further out than Pluto. 11 additional astronomical units that New Horizons, traveling faster than any human-made object in history, would require several more years to cross. The spacecraft flew past Pluto in July of 2015. It then continued outward, flying for another 3.5 years before reaching Arrokoth, a small Kuiper Belt contact binary, in January of 2019. And even after that encounter, New Horizons kept moving outward, still inside the belt, its nuclear power source slowly declining, its instruments still transmitting data across billions of kilometers of empty space back to receivers on Earth. That is what 20 astronomical units means when it is expressed not in numbers, but in time and motion. A spacecraft moving at tens of thousands of miles per hour, launched nearly 2 decades ago, is still crossing the territory that every standard diagram in existence represents as a thin strip at the edge of a poster. The distance is already overwhelming, but the volume of what that distance encloses is what truly breaks every expectation. Distance is one dimension. It is the easiest one to explain, the easiest one to illustrate with a ruler or a road trip analogy. But the Kuiper Belt does not exist in one dimension. It exists in 3. And the moment volume enters the conversation, every intuition built up through the previous comparisons collapses completely. Start with the planetary solar system, the region containing everything from Mercury out to Neptune's orbit. Model it as a sphere, which is a reasonable approximation, given that the planets orbit in a relatively thin plane but occupy 3-dimensional space when their full orbital paths are considered. The volume of that sphere, the region that contains every planet humanity has ever studied, every world any spacecraft has ever visited, every place in the solar system that appears on those familiar classroom diagrams, that entire volume is approximately 113,000 cubic astronomical units. 113,000 cubic astronomical units. It is a large number by any everyday standard, but it is the wrong number to look at in isolation. Numbers only reveal their meaning when placed next to other numbers. The classical Kuiper Belt extends from 30 astronomical units to 50 astronomical units. It is not a sphere. It is more like a shell, a thick ring wrapping around the outside of the planetary region. Calculate the volume of that shell from its inner boundary at 30 astronomical units to its outer boundary at 50 astronomical units, and the result is a number that is several times larger than the 113,000 cubic astronomical units that contains all the planets. The classical Kuiper Belt occupies more volume than the entire space enclosed by Neptune's orbit. Not slightly more, significantly more. Think about what that means in the most direct terms possible. Every planet in the solar system, every moon orbiting those planets, every spacecraft humanity has ever launched, every object that has ever appeared in a solar system diagram, all of it exists within a region of space that is smaller than the Kuiper Belt surrounding it. The container is smaller than the thing it sits inside. The comparison that makes this most visceral is simple. If the planetary solar system, the Sun and all 8 planets, and everything between them were a single room, the Kuiper Belt would not be a hallway outside that room. It would be an entire city surrounding the building that room sits in, not a neighborhood. A city. The room is real. It is significant. It contains everything familiar, but it is dwarfed by the urban expanse pressing in on every side of the building it occupies. And here is where the standard diagram fails in a second, less obvious way. Every diagram shows the Kuiper Belt as a flat ring, a two-dimensional strip lying in the same plane as the planets, encircling the Sun like a disk, like a wider version of Saturn's rings laid flat against the ecliptic. Clean, tidy, two-dimensional. The actual Kuiper Belt is nothing like that. Many of the objects within the Kuiper Belt, particularly those in the dynamically excited populations, the ones whose orbits were disturbed by Neptune's gravitational influence over billions of years, travel on paths that are significantly tilted relative to the flat plane of the planets. Orbital inclinations of 20 degrees, 30 degrees, even higher, are common among certain populations. These objects do not orbit neatly in the same plane as Earth or Jupiter. They swing up above that plane, arc over it, plunge back below it, tracing paths that carry them far from the thin disk where most planetary motion is concentrated. The effect of all those tilted orbits, accumulated across hundreds of thousands of objects, is that the Kuiper Belt puffs up into a structure that is thick in 3 dimensions. Not a flat ring, not a disk, something more like an enormous donut. A torus that is broad and rounded, denser near the ecliptic plane, and thinning out gradually above and below it, but extending a significant distance in the vertical direction as well as the radial one. At 50 astronomical units from the Sun, an orbital inclination of 30 degrees corresponds to a vertical displacement of 25 astronomical units above or below the ecliptic plane. 25 astronomical units. That is nearly the distance from the Sun to Uranus. Expressed now not as a horizontal span across the solar system, but as a vertical height above or below the plane in which the planets orbit. Objects in the Kuiper Belt can be as far above the ecliptic as Uranus is from the Sun. Has anyone ever pictured the Kuiper Belt as a flat ring, like a faint version of Saturn's rings scaled up to wrap around the whole solar system? Most people have. The diagrams invite exactly that image. They show the belt as a two-dimensional feature lying flat in the plane of the planets, giving no indication that it extends vertically into space in any significant way. The true structure, a thick, 3-dimensional torus of frozen material puffing upward and downward by distances measured in tens of astronomical units, is invisible in every standard depiction of the solar system. When all of this is taken together, the radial width of 20 astronomical units, the vertical extent generated by high inclination orbits, the full 3-dimensional shell of space that Kuiper Belt objects actually inhabit, the volume of the region becomes something that resists ordinary language. The numbers exist. They can be written, but they do not land the way numbers usually land because there is no human experience scaled appropriately to receive them. Every time these numbers are encountered directly, something strange happens. Not fear exactly, but something that functions like being physically reduced. Like the mind briefly grasps the true scale and the self becomes correspondingly smaller against it, in the most literal sense imaginable, but a region of space this enormous containing within it almost nothing. The Kuiper Belt occupies more volume than the entire planetary solar system. That much is now established. The natural next assumption, the one the mind reaches for almost automatically, is that something filling that much space must be crowded with objects, dense, packed, the way a forest fills its territory with trees, or a city fills its footprint with buildings. That assumption is wrong, completely, counterintuitively, almost absurdly wrong. Astronomers estimate that the Kuiper Belt contains approximately 100,000 objects larger than 100 kilometers in diameter. 100 kilometers is roughly 62 miles, about the driving distance from one end of a major metropolitan area to the other. These are not small pebbles. They are bodies the size of small nations, substantial enough to have detectable gravity, substantial enough to be candidates for study by even moderately powerful telescopes if they were close enough. 100,000 of them, scattered across the classical belt. Beyond those, there are estimated to be millions of objects in the range of 1 to 100 kilometers. And beyond those, extending down to fragments just meters across, there may be trillions of smaller icy bodies, remnants from the solar system's formation, preserved in the deep cold, too small to detect individually with any current instrument, but present in numbers that strain the vocabulary of large quantities. 100,000 large objects, millions of medium ones, trillions of small fragments. It sounds, on paper, like a crowded place. It is not. Take the estimated population of significant Kuiper Belt objects, the ones large enough to matter, the ones in the range of a few kilometers and above, and distribute them evenly through the volume of the classical belt. Calculate how much space each one gets. The result is staggering. The average distance between any given Kuiper Belt object and its nearest neighbor works out to tens of millions of miles, not thousands of miles, not hundreds of thousands, tens of millions. The closest approach distance between Earth and Mars, the moment every few years when the two planets are at their nearest point in their respective orbits, is approximately 34 million miles. The average gap between neighboring Kuiper Belt objects is comparable to that distance. Every object in the belt is separated from the next one by roughly the distance between two planets. When New Horizons crossed the Kuiper Belt, it did not navigate through a field of obstacles. There was nothing to navigate. The spacecraft flew through billions of miles of essentially unobstructed space, encountering no debris, no hazards, no objects close enough to register as anything other than distant specks. And even those specks were only detectable because astronomers knew precisely where to point the instruments. The belt that sounds, from population estimates, like it should be a dense field of frozen debris, was in practice indistinguishable from empty space to a spacecraft flying through it. Finding Arrokoth, the small contact binary that New Horizons visited in January of 2019, required years of dedicated searching using the Hubble Space Telescope. After the Pluto flyby in July of 2015, mission scientists needed to identify a Kuiper Belt object close enough to New Horizons' outbound trajectory to be reachable with the fuel remaining on board. They searched systematically, scanning patches of sky, comparing exposures taken on different nights, looking for the faint, slow-moving points of light that indicate something nearby rather than a distant star. The search took years. The target, when finally identified, required precise course corrections to reach. Without those corrections, without that deliberate, years-long effort to find and aim for a specific object, New Horizons could have crossed the entire classical Kuiper Belt without coming within millions of miles of anything worth observing. If you can hold that image clearly, a spacecraft the size of a grand piano, moving at tens of thousands of miles per hour, crossing a region containing 100,000 large objects and trillions of smaller ones, and finding that region effectively indistinguishable from empty space. Then the true density of the Kuiper Belt begins to register. An analogy that comes close: imagine a warehouse the size of a small city. Not a building, a warehouse that covers the entire footprint of a city, stretching from one end to the other in every direction, its interior open and unlit. Inside that warehouse, someone has scattered a handful of marbles, not thousands of marbles, a handful, and those marbles are the only objects in the entire space. Now, walk into that warehouse and try to find one without a map, without a flashlight pointed at the right spot, without any prior knowledge of where any marble was placed. Walk for an hour, walk for a day, walk for a week. The probability of stepping on a marble, or even coming close enough to one to see it in the dimness, is vanishingly small. Not impossible, but close enough to impossible that the distinction barely matters. That is the interior of the Kuiper Belt, scaled down to something a body can move through. If the Kuiper Belt is this empty, why do we still call it a belt? The name carries connotations that the reality does not support. A belt implies something continuous, something that wraps and holds, something with a presence that can be felt. The Kuiper Belt is continuous only in the sense that its objects share a general region of space. It wraps around the sun in the sense that its members orbit in a broadly disk-like distribution. But felt, no. A spacecraft moving through it feels nothing. The objects are there, but they are islands separated by oceans so wide that the word ocean does not do the distance justice. Empty space is not what makes the Kuiper Belt scientifically irrelevant. The opposite is true. Empty space is not what makes the Kuiper Belt irrelevant, because what remains inside that emptiness is something that cannot be found anywhere else in the solar system. The objects drifting through the Kuiper Belt are not random debris. They are not the leftovers of something that broke apart, not the remnants of a collision, not the scattered fragments of a world that failed to hold itself together. They are something far more significant than any of that. They are the original material, the unedited, unprocessed, unaltered substance from which the entire solar system was built. 4.5 billion years ago, preserved in a cold so extreme that time itself seems to have lost its grip on them. 4.5 billion years. That number appears often enough in discussions of solar system science that it can start to feel routine. It should not. 4.5 billion years ago, there were no planets. There was no Earth, no moon, no continents, no oceans. There was a young star the sun surrounded by an enormous rotating disk of gas and dust, and within that disk, tiny solid grains were beginning to collide, stick together, and slowly accumulate into larger and larger bodies. The inner regions of that disk were warm enough that only rock and metal could survive as solids. Further out, where the temperature dropped below the freezing points of various compounds, ices began to form. Water froze first, then carbon dioxide, then methane, then nitrogen, then carbon monoxide, layer by layer, molecule by molecule. The cold outer disk became a reservoir of frozen chemistry, every volatile compound that existed in the young solar nebula condensing out of the gas phase and coating the tiny solid grains accumulating in the darkness beyond the frost lines. The Kuiper Belt formed from that material, and unlike the inner solar system, where geological processes, volcanism, plate tectonics, erosion, impact gardening, atmospheric chemistry, have continuously reworked the surfaces and interiors of the planets for billions of years, the outer solar system has been cold and quiet. The Kuiper Belt objects that formed in that early disk have been sitting in temperatures close to absolute zero ever since, barely disturbed, barely processed, barely changed. The composition of these objects reflects exactly where and how they formed. Water ice is the structural backbone of most Kuiper Belt bodies, the most abundant solid compound in the outer solar nebula, the foundation on which everything else is layered. Mixed into and frozen onto that water ice are methane, nitrogen, carbon monoxide, carbon dioxide, and ammonia compounds that exist as gases in the inner solar system that evaporate instantly under the warmth of sunlight at Earth's distance from the sun, but that at 40 or 50 astronomical units freeze as hard and permanent as granite. Then there are the organic compounds, complex carbon-based molecules built up through radiation chemistry in the outer reaches of the solar nebula, coating the surfaces of Kuiper Belt objects in dark, reddish material called tholins. These compounds are not alive, but they are the kind of chemistry that preceded life on Earth, the kind of molecular building blocks that planetary scientists believe were delivered to the early inner solar system by comets and small bodies originating in the cold outer regions. The Kuiper Belt is, among other things, an archive of prebiotic chemistry frozen in place since before the Earth existed. Surface temperatures on these objects sit at approximately -220 degrees Celsius. To put that in terms that carry some weight, liquid nitrogen, the substance used in laboratories to freeze biological samples and shatter rubber with a single tap boils at -196 degrees Celsius. Kuiper Belt objects are colder than that. At -220 degrees, methane does not bubble or flow. It does not behave like a gas or even like a liquid. It freezes into a solid that is rigid and hard, indistinguishable in its physical behavior from rock. Nitrogen does the same. Carbon monoxide does the same. Everything that would be a gas or a liquid anywhere in the inner solar system becomes, at these temperatures, a solid as unyielding as stone. And in that extreme cold, nothing changes. There is no liquid water to drive chemical reactions. There is no volcanic heat to resurface terrain. There is no atmosphere thick enough to generate weather that erodes or deposits material over geological timescales. The interiors of these objects are too cold and too small to sustain the radioactive decay that drives geological activity in larger bodies. They simply sit, they orbit, they accumulate the occasional small impact, the slow darkening of their surfaces from cosmic radiation, the gradual processing of their outermost molecular layers by high-energy particles streaming in from the sun and from interstellar space. But the bulk of the object, the interior, the structure, the chemical composition, remains as it was when the body first assembled itself from colliding grains in the early solar nebula. This is what makes Kuiper Belt objects categorically different from anything in the inner solar system. Earth has been geologically active for its entire existence. Its surface has been repeatedly remade by plate tectonics, volcanism, and the slow grinding of atmospheric and oceanic erosion. Mars has ancient volcanic plains and impact basins that have been reworked by wind and seasonal frost cycles over billions of years. Even the Moon, geologically quiet for most of its history, was resurfaced by volcanic flooding during its first billion years. Every rocky body close to the Sun carries the marks of processes that have been operating continuously since the solar system formed, layering change upon change until the original material is buried or transformed beyond recognition. A Kuiper Belt object carries none of those layers. Its surface is old, certainly marked by small craters accumulated over billions of years of occasional impacts with other debris, but the material beneath that surface is pristine. It is the original substance of the outer solar nebula, unmelted, unmetamorphosed, unprocessed by anything except the slow work of cosmic radiation on its outermost skin. Looking at a Kuiper Belt object is not like looking at a planet that formed at the same time. It is like finding the original manuscript of a document that has been copied, edited, translated, revised, and reprinted so many times that no one alive has ever seen the first version. The planets are the reprints. The Kuiper Belt objects are the manuscript. That is what makes the Kuiper Belt sacred in a way that has nothing to do with beauty or scale. Not sacred in any mystical sense, but in the sense that it is honest. It has not been altered to fit later conditions. It has not been revised by heat or pressure or time. It holds the original text of the solar system's formation in its frozen chemistry, waiting for instruments precise enough to read it. Every spacecraft sent to the outer solar system, every spectrum taken of a Kuiper Belt object's surface, every measurement of its density or composition or orbital history is an act of reading that original text slowly, one word at a time, across billions of kilometers of empty space. This is what the Kuiper Belt actually is. Stripped of all the scale comparisons and volume calculations and travel time analogies, it is a library, an unheated, unlit, 4.5 billion-year-old library, with its holdings scattered across 30 billion kilometers of frozen darkness. Each object a document written in ice and organics and silicate dust, encoding information about conditions that no longer exist anywhere else in the solar system. But those frozen islands are not simply inert rocks. Drifting in silence, some of them have mountains, atmospheres, and geology that is still active right now. For 76 years, it had a title, the 9th planet, the outermost world, the cold-aged distant sentinel at the edge of the solar system. Discovered in 1930 by a young astronomer named Clyde Tombaugh, working at the Lowell Observatory in Arizona, scanning photographic plates night after night until a faint moving speck revealed itself against the fixed background of stars. Pluto was celebrated, named, assigned a symbol, given a place on every solar system diagram printed for the better part of a century. School children memorized its position. Its name became embedded in popular culture in ways that no other astronomical body, except perhaps the Moon, has ever quite managed. Then, in 2006, the International Astronomical Union voted Pluto was reclassified as a dwarf planet. The 9th planet became the first and largest member of a newly defined category, and the solar system officially shrank to 8 worlds. The public reaction was something between grief and outrage. Letters were written, petitions were signed. The state of New Mexico, where Tombaugh was born, passed a resolution declaring that Pluto remains a planet within its borders. The demotion became a cultural moment, a rare instance of an astronomical decision generating genuine emotional response from people who had never previously spent much time thinking about planetary classification criteria. But the reclassification itself is not the most interesting part of the story. The most interesting part came 9 years later, when New Horizons arrived. July 2015. After 9.5 years of flight, after crossing more than 4.5 billion kilometers of interplanetary space, the spacecraft made its closest approach to Pluto, passing within about 12,500 kilometers of the surface, moving at approximately 49,000 kilometers per hour, with only minutes to collect the data that scientists had been waiting decades to see. The images began arriving on Earth hours later, transmitted across the vast distance at the speed of light, each one taking more than 4 hours to make the journey. What they showed stopped people cold. Pluto was not the dead, featureless ice ball that most planetary scientists had quietly assumed it would be. The images revealed a world of extraordinary diversity, a surface covered in dramatically different terrain types, textures, and colors, more varied in its geography than anyone had predicted for a body this small, this cold, this far from the sun. There were dark reddish regions near the equator, ancient and heavily cratered. There were bright polar deposits, and dominating the face of Pluto that New Horizons imaged most closely was an enormous bright feature shaped roughly like a heart, spanning more than 2,000 kilometers across, later named Tombaugh Regio, in honor of the man who found it. The left lobe of that heart is called Sputnik Planitia. It is a basin of frozen nitrogen ice covering an area larger than the state of Texas, and its surface is almost completely free of impact craters. That absence is not a minor detail. It is the most scientifically significant feature New Horizons found on Pluto. On any world that has been sitting in the outer solar system for 4.5 billion years, impact craters should accumulate continuously. Space is not empty of small debris, and over geological timescales, even a slow rate of impacts adds up to a heavily cratered surface. The fact that Sputnik Planitia shows almost no craters means only one thing: something is erasing them. The surface is being continuously renewed, reshaped, repaved. The nitrogen ice is not static, it is moving. Scientists determined that the frozen nitrogen in Sputnik Planitia is undergoing convection, the same process that drives circulation in Earth's mantle, where warmer material rises and cooler material sinks, turning over slowly in giant cells. On Pluto, the nitrogen ice is slightly warmer at depth than at the surface, just warm enough to become buoyant, just warm enough to rise, spread across the surface, cool, sink again, and repeat. The time scale of each convective cycle is estimated at hundreds of thousands of years. By geological standards, that is fast. Fast enough to erase craters, fast enough to qualify, without any ambiguity, as active geology. Active geology. On a world sitting 5.9 billion kilometers from the sun, receiving sunlight 900 times weaker than what reaches Earth's surface. A world where the surface temperature hovers around negative 220 degrees Celsius. A world that most planetary scientists had mentally filed under geologically dead before New Horizons arrived. Alongside the nitrogen plains, New Horizons found mountains, not gentle hills mountains. Water ice peaks rising up to 3,300 meters above the surrounding terrain, comparable in height to significant ranges on Earth. At Pluto's surface temperatures, water ice behaves like rock, rigid enough to support mountain ranges over geological ages, while the softer nitrogen and methane ices flow around and between them. Then there is the atmosphere. Pluto has one thin, primarily nitrogen, with traces of methane and carbon monoxide, expanding slightly when Pluto is closer to the Sun and contracting as it moves outward along its elliptical orbit. When New Horizons looked back after its closest approach, imaging Pluto with the Sun behind it, the spacecraft captured something remarkable. Layers of haze extending hundreds of kilometers above the surface, backlit by sunlight, delicate and structured, created by ultraviolet radiation, breaking apart methane molecules in the upper atmosphere and driving the formation of complex hydrocarbon compounds that settle slowly downward, giving Pluto its characteristic reddish-brown tones in certain regions. And then there is Charon, Pluto's largest moon, with a diameter of about 1,212 kilometers, roughly half of Pluto's own diameter of about 2,377 kilometers. That ratio is extraordinary. No other planet in the solar system has a moon so large relative to itself. The gravitational consequence is that Pluto and Charon do not orbit each other in the conventional sense, where a small moon circles a much larger planet. Instead, they orbit a shared center of mass, a barycenter that lies in the empty space between them. Outside Pluto's surface entirely, they are, by any reasonable physical definition, a binary system. Two worlds locked face to face, each keeping the same side permanently turned toward the other, circling their common point of balance in the darkness together. If Pluto is no longer a planet, why does it turn out to be more geologically interesting than several planets that kept their titles? That question does not have a clean answer. What it has is a lesson. Classification is a human convenience, and nature does not sort itself according to human convenience. Pluto is whatever it is, regardless of what category it occupies in a taxonomy. And what it is, as New Horizons revealed, is a world of genuine complexity, active, layered, surprising, and far from finished revealing what it contains. But Pluto is only the most famous object in the Kuiper Belt, not the largest, and not the strangest. The discovery that ended Pluto's planetary status did not come from a committee meeting or a change in philosophical preference. It came from a telescope on Palomar Mountain in California in 2005, when astronomer Mike Brown and his team detected a bright object moving slowly against the background stars in a region of sky far beyond Neptune's orbit. The object was distant, cold, and when its size was eventually determined comparable to Pluto itself, it was named Eris, after the Greek goddess of discord. The name proved apt. Eris is slightly smaller than Pluto in diameter, measuring approximately 2,326 kilometers across. But diameter is not the same as mass. Eris is approximately 27% more massive than Pluto, packing significantly more material into a slightly smaller volume. The resulting density is higher. Eris contains a greater proportion of rock relative to ice than Pluto does, making it a denser, heavier object despite its smaller cross-section. When scientists first calculated Eris's mass and compared it to Pluto's, the implications for planetary classification became unavoidable. If Pluto was a planet, then Eris more massive, comparably sized, orbiting the Sun in the same general region, would also have to be a planet. And if both were planets, the list would not stop there. The Kuiper Belt clearly contained other large objects. The solar system was either about to gain many new planets, or it needed a new definition. The International Astronomical Union chose the definition. Eris's orbit is nothing like Pluto's relatively modest ellipse. It swings from approximately 38 astronomical units at its closest approach to the Sun, out to approximately 97 astronomical units at its farthest a range that carries it well beyond the classical Kuiper Belt's outer edge at 50 astronomical units, deep into the scattered disk population. Its orbital period is 559 Earth years. For most of that orbit, Eris is not somewhere near the classical belt where Pluto and the other familiar Kuiper Belt objects reside. It is somewhere in the distant outer reaches, retreating toward distances that put it nearly 100 times farther from the Sun than Earth. At that distance, even Pluto's meager sunlight would feel comparatively warm. Eris receives almost nothing. Whatever atmosphere it might possess is almost certainly frozen completely onto its surface for the majority of its centuries-long orbit, too cold to sublimate into even the thinnest gas. It has one known moon, Dysnomia, which orbits it once every approximately 15.8 days. The existence of that moon is what allowed scientists to calculate Eris's mass precisely by measuring Dysnomia's orbital period and distance. They could apply basic gravitational physics and determine the mass of the system with high confidence. Makemake was discovered in 2005 as well. In the weeks following the announcement of Eris, it orbits at an average distance of approximately 45.8 astronomical units, well within the classical Kuiper Belt, and has a diameter of roughly 1,430 kilometers, making it about 60% of Pluto's size. Its surface is covered in frozen methane and ethane, giving it a pale, slightly reddish appearance, and possibly frozen nitrogen as well, though in smaller quantities than Pluto. Like Pluto and Eris, its surface is colored in places by tholins, those dark organic compounds built up through radiation processing of surface ices over billions of years. For years after its discovery, Makemake appeared to have no moon, an unusual characteristic for a body of its size, since gravitational captures and collision-generated satellites are common among large Kuiper Belt objects. Then, in 2016, images taken by the Hubble Space Telescope revealed a small and dark companion, provisionally designated MK2. The moon's darkness, its very low reflectivity compared to Makemake's bright surface, suggested it has a different surface composition, possibly lacking the fresh methane ice that gives Makemake its relatively high albedo. The discovery added Makemake to the growing list of Kuiper Belt dwarf planets known to host at least one satellite. And then there is Haumea, which is not round. Most sufficiently massive objects in the solar system are round, or very close to it. Gravity pulls material inward equally in all directions, and above a certain size threshold, any irregular shape gets pulled into a sphere by its own weight. Haumea is large enough that gravity should have done exactly that. Instead, it looks like an egg stretched dramatically along one axis, an elongated ellipsoid, roughly 1,920 kilometers along its longest dimension, and only about 1,000 kilometers along its shortest. It is shaped less like a planet and more like an American football that has been squeezed at both ends. The cause of this shape is rotation. Haumea completes one full rotation every 3.9 hours, one of the fastest rotation rates of any large object in the solar system. At that speed, centrifugal effects fling material outward along the equator, stretching the body dramatically and preventing gravity from pulling it into a sphere. The rapid spin is thought to be the result of a large impact early in Haumea's history, the same collision that likely produced its two known moons, Hi'iaka and Namaka, by ejecting material that then coalesced into satellites. Did you know that beyond Saturn, there are other objects in the solar system that also have rings? Haumea does. In 2017, astronomers observed Haumea passing in front of a distant star, a stellar occultation, and the careful measurement of how the star's light dimmed. Before and after the main body blocked it, revealed a narrow ring of material orbiting Haumea at a distance of approximately 2,287 kilometers from its center. Haumea became the first known trans-Neptunian object with a confirmed ring system, and the only dwarf planet known to possess one. The ring is thought to be composed of debris, possibly material ejected during the same ancient collision that shaped Haumea's current form and produced its moons. 3 dwarf planets, 3 radically different stories: Eris, dense and massive, retreating to the far edges of the scattered disk for centuries at a time; Makemake, pale and methane-covered, sitting quietly in the classical belt with its newly discovered dark companion; Haumea, spinning so fast it cannot hold its own shape, ringed and elongated, a record of violence frozen in its geometry. These worlds are overwhelming in their own right, but they were placed into their current orbits by a single force that reshaped the entire outer solar system. On January 1st, 2019, at approximately 12:33 in the morning Eastern Time, New Horizons made its closest approach to a small object orbiting the Sun at approximately 44.6 astronomical units deeper into the Kuiper Belt than Pluto, further from Earth than any spacecraft had ever deliberately targeted before. The object had been known by a temporary designation during the years of searching and approach. It was later given the name Arrokoth, from the Powhatan and Algonquian language, meaning sky. At the moment of closest approach, the signal confirming the flyby's success took more than 6 hours to travel back to Earth at the speed of light. The team at the Johns Hopkins Applied Physics Laboratory waited through those hours, knowing the spacecraft had either succeeded or failed long before they would learn which. It had succeeded, and what it found was unlike anything the mission scientists had seen before, not because it was dramatic, but because it was the opposite of dramatic, because it was, in the most precise scientific sense possible, untouched. Arrokoth is a contact binary, 2 roughly spherical lobes, joined at a narrow neck, sitting in contact with each other like a snowman built from 2 mismatched balls of snow. The larger lobe, named Wenyu, measures approximately 22 kilometers across. The smaller lobe, named Weo, is approximately 15 kilometers in diameter. Together, they stretch approximately 35 kilometers from end to end, a body small enough that it would fit comfortably within the boundaries of a mid-sized American city. yet one that has been orbiting the Sun unchanged since before the Earth existed. The shape itself is the first message. Contact binaries form when two separate objects, orbiting close to each other as a gravitationally bound pair, gradually spiral together and merge. The key word is gradually. A violent collision at high velocity does not produce a gentle contact binary. It produces fragments, craters, debris fields, shattered surfaces, and objects whose internal structure bears the marks of catastrophic impact. Arrokoth shows none of that. Its two lobes fit together smoothly at the neck. There are no fractures radiating outward from the contact point. No material has been blasted away and scattered into the surrounding space. No angular, broken edges mark the junction. The merger that created Arrokoth happened at a speed of a few kilometers per hour. Not thousands of kilometers per hour. The way a comet strikes a planet? A few kilometers per hour, the speed of a person walking briskly, or a bicycle moving gently down a shallow slope. Two objects, each a few kilometers across, drifting slowly toward each other in the cold outer solar nebula, drawn together by their mutual gravity over timescales measured in thousands of years, finally making contact so gently that neither was broken by the encounter. Two bubbles touching, not two rocks colliding. This tells planetary scientists something profound about how small bodies in the outer solar system form. The prevailing model before Arrokoth held that accretion, the process by which small objects stick together and grow into larger ones, happened primarily through random collisions driven by the relative velocities of objects moving through the disk. Arrokoth's structure is inconsistent with that model at the scale of its formation. The gentleness of its merger points instead toward a process called pebble cloud collapse or streaming instability, in which local concentrations of small solid particles in the solar nebula collapse gravitationally into bound clusters, and those clusters then coalesce slowly into larger bodies without the violent randomness of high-speed collisions. The surface of Arrokoth is uniformly reddish-brown, every part of it, both lobes, the neck, the entire visible surface shares the same color, the same spectral signature, the same composition fingerprint. That uniformity is itself significant. It indicates that both lobes formed from the same reservoir of material in the same region of the solar nebula, at the same time, under the same conditions. They were siblings before they were merged into a single body, born from the same cloud of collapsing particles and bound to each other gravitationally from their earliest existence. The color comes from tholins, the same radiation-processed organic compounds found on Pluto, on Charon's polar cap, on the surfaces of countless other Kuiper Belt objects. Cosmic rays and ultraviolet photons streaming through the outer solar system have been slowly converting the simple ices on Arrokoth's surface into complex organic molecules for 4.5 billion years, building up a dark reddish crust that absorbs rather than reflects the faint sunlight reaching it at 44 astronomical units. Beneath that surface crust, the interior of Arrokoth has almost certainly remained unchanged since the body first assembled itself. No geological heat has processed it. The body is too small for radioactive decay in its interior to have generated significant warming. No large impact has fractured and rearranged its structure. It has not passed close enough to the Sun at any point in its history to experience significant thermal processing. It has simply orbited, cold and intact, through 4.5 billion years of solar system history, accumulating its thin coating of organic material on the outside while preserving the original composition of the outer solar nebula within. Is there anything on Earth that has survived 4.5 billion years without changing? The answer is essentially no. The oldest known intact mineral grains on Earth zircon crystals, found in Western Australia, date to approximately 4.4 billion years ago, making them among the most ancient materials on the planet. But even those crystals formed after the Earth itself had already differentiated, already been reshaped by the moon-forming impact, already begun the geological processing that would continue for billions of years afterward. They are old by Earth standards. By Arrokoth's standard, they are products of a world that had already been through tremendous upheaval by the time they crystallized. Arrokoth is not extraordinary because it is large or violent or dramatic. It is extraordinary because it is honest to a degree that is almost impossible to find anywhere else in the solar system. 4.5 billion years, and nothing changed. That kind of fidelity to an original state, that kind of stubborn, quiet persistence through all the time that has passed since the solar system began is not beauty. It is something rarer than beauty. But Arrokoth did not simply drift into its current position by accident. The entire architecture of the Kuiper Belt is the result of a violent cosmic migration whose traces are still written everywhere today. The Kuiper Belt is not a single, uniform population of objects sharing similar histories and similar orbits. It is more like a city in which several entirely different communities happen to occupy the same geographic area, each with its own origin story, its own dynamics, its own relationship to the forces that shaped the outer solar system. 3 major orbital families define the belt's structure, and each one tells a different chapter of the same larger story. The first and most undisturbed family are the classical Kuiper Belt objects, informally called Kubawanos, a name derived from the designation of the first confirmed member of this group, 1992 QB1, the first Kuiper Belt object discovered after Pluto. The pronunciation of QB1 eventually morphed into Kubiwano, and the name attached itself to the entire population. These objects orbit the Sun at distances ranging from roughly 42 to 48 astronomical units, on paths that are relatively circular and relatively close to the ecliptic plane. They are the residents who were already there before anything else arrived, the ones whose orbits have been least disturbed by the gravitational upheavals of solar system history. Within the Kubawanos, astronomers have identified 2 distinct subpopulations, called cold and hot terminology that refers not to temperature, since everything in the Kuiper Belt is frozen solid regardless of orbital classification, but to the character of the orbits themselves. Cold classical objects travel on nearly circular orbits with low inclinations, rarely straying more than 5 degrees above or below the ecliptic plane. They tend to be redder in color than other Kuiper Belt populations, their surfaces more deeply processed by billions of years of cosmic radiation exposure without any interruption from geological activity or collisional resurfacing. They also show an unusually high rate of binary pairs, 2 objects orbiting each other as they jointly circle the Sun, which indicates they formed in a low-velocity environment where gravitational capture between neighboring objects was possible without immediate disruption. The cold classical objects are, by all evidence, the genuine locals. They formed where they are, and they have stayed there. Hot classical objects, by contrast, travel on more elliptical paths with higher inclinations, some exceeding 20 or 30 degrees from the ecliptic. Their colors are more varied, their surfaces less uniformly red, their binary fraction lower. Everything about their orbital properties suggests they did not form in the calm, circular orbits they currently occupy. They were disturbed, excited, pushed into their present configurations by gravitational forces that stirred up the outer solar system at some point in its early history. The second major family are the Plutinos, named for their most famous member. Plutinos are locked in what orbital mechanics calls a 3-to-2 mean motion resonance with Neptune. For every 3 complete orbits Neptune makes around the Sun, a Plutino completes exactly 2, not approximately 2. Exactly 2, maintained with extraordinary precision by the continuous gravitational interaction between the object and Neptune. Pluto itself sits in this resonance. Its orbital period is approximately 248 Earth years. Neptune's is approximately 165 years. The ratio between those periods is essentially 3-to-2. maintained across billions of years by the resonance lock that Neptune's gravity imposes. The consequence of this lock is one of the most counterintuitive facts in solar system dynamics. Pluto's orbit actually crosses Neptune's orbit. At its closest approach to the Sun, Pluto comes to approximately 29.7 astronomical units inside Neptune's average orbital distance of 30 astronomical units. The two orbits intersect on a diagram. Any reasonable intuition about what happens when two orbiting bodies share overlapping paths would suggest that eventually they must come close to each other, and that a close encounter would disrupt or destroy one of them. If Pluto and Neptune have crossing orbits, why have they never collided in 4.5 billion years? The 3-to-2 resonance prevents it. Because of the precise timing that the resonance enforces, whenever Pluto is at its closest point to the Sun, the point where it crosses inside Neptune's orbit, Neptune is always on the opposite side of its own orbit, roughly half an orbit away, separated from Pluto by billions of kilometers. The resonance acts as a gravitational traffic signal, coordinating the timing of their orbital positions so perfectly that the two bodies are never in the same part of space at the same time. Despite their paths nominally intersecting, in 4.5 billion years, that signal has never failed. The third family. The scattered disk is where the violence of Neptune's influence becomes most visible. Scattered disk objects are not gently displaced or locked into stable resonances. They were thrown. At some point in the past, each of these objects had a gravitational encounter with Neptune close enough and powerful enough to dramatically alter its orbit, flinging it outward onto a path that carries it far from the relatively ordered zone of the classical belt. Their closest approaches to the Sun sit in the range of 30 to 35 astronomical units, near Neptune's orbit, the scar of the encounter that ejected them, but their farthest points can reach 100, 200, even 500 astronomical units from the Sun. They spend the overwhelming majority of their centuries-long or millennia-long orbits in the distant outer reaches, retreating deep into darkness before slowly falling back inward. Eris is the most massive, known scattered disk object. Its orbit, ranging from 38 astronomical units at closest approach to 97 astronomical units at its farthest, is a direct record of the gravitational kick that Neptune delivered to it at some point in the distant past. That kick sent Eris onto a path that carries it nearly 100 astronomical units from the Sun at its most distant, well beyond the classical belt, into a region so remote that even Pluto's sparse sunlight would feel comparatively abundant. Eris is, in the most literal orbital sense, proof of what Neptune is capable of. These orbits are not accidental. They are frozen evidence of a cosmic catastrophe that unfolded billions of years ago. For most of the 20th century, planetary scientists operated under an assumption so fundamental that it rarely needed to be stated explicitly. The solar system, in its broad architecture, had always looked roughly the way it looks now. The giant planets formed where they orbit today. The Kuiper Belt assembled itself in the region beyond Neptune where we currently find it. The whole system settled into its present configuration early in its history and had been sitting there, largely unchanged, for the past 4.5 billion years. It was a comfortable assumption. It made the solar system feel stable, ordered, comprehensible, a system that had found its equilibrium and kept it. Computer simulations destroyed that assumption. When planetary scientists in the late 1990s and early 2000s began building sophisticated models of solar system formation models that started from realistic initial conditions and let gravitational physics run forward in time, they ran into a persistent, troubling problem. The models that assumed Neptune had always been at 30 astronomical units could not reproduce the Kuiper Belt structure that actually exists. The predicted distributions of objects were wrong. The orbital characteristics came out wrong. The ratio of objects in various resonances did not match observations. The total mass in the belt was off, no matter how the starting parameters were adjusted. A solar system with Neptune fixed at 30 astronomical units from the beginning produced a Kuiper Belt that looked nothing like the one telescopes were revealing. Something was missing from the picture, something fundamental. The solution came from a group of researchers working in Nice, France, at the Côte d'Azur Observatory, who published a series of papers in 2005 proposing what became known as the Nice model. The core idea was radical. In its simplicity, the giant planets did not form where they are today. They formed much closer together, in a more compact configuration, and then migrated outward to their current positions over tens of millions of years through gravitational interactions with a massive disk of icy bodies that surrounded them. In the Nice model's initial configuration, all 4 giant planets, Jupiter, Saturn, Uranus, and Neptune, are packed within a range of approximately 15 to 20 astronomical units from the Sun. They are closer together than any of them are today. Their orbits are more circular, more orderly, more mutually stable in their compact arrangement. And beyond them, extending outward for many astronomical units in every direction, lies a massive disk of icy planetesimals, small bodies left over from planet formation, the raw material of the outer solar system that never got incorporated into a planet. This disk is not the thin, sparse Kuiper Belt we see today. It is enormous. Its estimated total mass is somewhere between 35 and 50 times the mass of Earth, compared to the roughly 1/10 of Earth's mass that the current Kuiper Belt contains. The system begins to evolve when gravitational interactions between the giant planets and the outer disk start exchanging energy and angular momentum. Jupiter, the most massive body in the system, slowly migrates inward, losing energy to the disk material it encounters. Saturn, Uranus, and Neptune, further out and interacting with the outer portions of the disk, gain energy and migrate outward. The process is slow by human standards, tens of millions of years, but relentless. And at some point, according to the model, Jupiter and Saturn cross through a critical orbital ratio. Their periods pass through a 2-to-1 resonance with each other, a gravitational configuration that pumps energy into the orbits of Uranus and Neptune and destabilizes the entire outer system. What follows is the event that defines everything. Uranus and Neptune are kicked outward dramatically, their orbits becoming more elliptical, their trajectories carrying them plunging into the thick outer disk. Neptune, starting from somewhere around 20 astronomical units, possibly even closer, begins a long outward migration that will not end until it reaches approximately 30 astronomical units, its current position, where the disk has been sufficiently depleted to bring the migration to a halt. The word migration makes it sound orderly. It was not. Neptune, moving outward through a disk containing 35 to 50 Earth masses of icy planetesimals, is not a planet gently drifting through empty space. It is something closer to a plow, a gravitational plow of enormous mass, sweeping through a densely populated region, interacting with every body it encounters. Some of those bodies get captured into resonances. As Neptune moves outward, its resonance zones move with it, sweeping through the disk like a net dragged through water. Objects that happen to be at the right distance at the right moment get swept up into the moving resonance and carried outward along with Neptune, locked into the precise orbital relationship that protects them from further disruption. These are the Plutinos, captured resonant objects that rode Neptune's outward migration and have been locked into the 3-to-2 resonance ever since. Pluto itself was almost certainly captured this way. It did not form at 39 astronomical units. It was placed there by Neptune's motion. Other objects are not so fortunate. Those that encounter Neptune without being captured into a resonance receive gravitational kicks that send them onto highly elliptical orbits, scattered outward to enormous distances, becoming the scattered disk objects whose extreme trajectories we now observe. Eris, with its orbit swinging between 38 and 97 astronomical units, is a direct product of this scattering. Its orbital shape is a preserved record of the encounter that threw it. And most objects, the vast, overwhelming majority of everything in that original disk, are simply ejected. Neptune's repeated gravitational interactions over tens of millions of years throw body after body onto orbits that escape the solar system entirely. They cross the threshold of Neptune's gravitational influence and keep going, disappearing into interstellar space, lost forever. Others are thrown inward rather than outward, crossing into the realm of the giant planets and ultimately being swallowed by Jupiter or the Sun, or ejected inward toward the rocky planets where they contribute to a period of intense bombardment in the inner solar system. The accounting is staggering. When Neptune's migration finally ends, when the disk has been sufficiently cleared for the planet to settle into its current stable orbit, more than 99% of the original disk mass has been removed, ejected to interstellar space, swallowed by planets, thrown into the Sun. The disk that once held between 35 and 50 Earth masses of icy material has been reduced to approximately 1/10 of one Earth mass. The Kuiper Belt we see today is not the structure that existed before Neptune's migration. It is the wreckage that survived it, the 1% of the original population that managed to find a stable configuration, whether through resonance capture or by occupying the distant cold classical zone that Neptune's migration did not fully reach. Knowing that the solar system was once this chaotic, does its current stability feel more remarkable to you? It should. The calm, orderly arrangement of 8 planets in roughly circular orbits, the stable resonances of the Kuiper Belt, the quiet drift of the cold classical objects in their undisturbed paths. None of this is the natural resting state of a planetary system. It is the outcome of a prolonged catastrophe that eliminated nearly everything, leaving behind a highly selected survivor population organized into the structures we now observe. The stability is real, but it was purchased at an enormous cost, paid in the destruction of the vast majority of the solar system's original outer material. The Kuiper Belt is not a legacy, it is a ruin. And sometimes ruins speak more honestly than anything left standing. So the Kuiper Belt is the remnant of a different solar system. But the story does not end here, because beyond it lie layers of mystery that not even light has yet brought back information from. There is a tendency, when learning about the Kuiper Belt, to think of it as a defined region with clear edges, a zone that begins at 30 astronomical units, where Neptune's orbit ends and stops at 50 AU, where the classical belt thins out. That mental image of a bounded territory, a ring with an inner wall and an outer wall, is clean and satisfying. It is also wrong in a way that becomes more significant the further out one looks. The classical Kuiper Belt does thin out around 50 astronomical units. The density of objects drops, the population becomes sparser, and the organized structure of the classical belt, with its distinct cold and hot populations, its resonant clusters, its relatively well-defined orbital families begins to dissolve. But there is no wall, no sharp boundary, no line in space where the belt ends and something else begins. The transition is gradual, a fading rather than a stopping. And what lies beyond 50 astronomical units is not empty space awaiting discovery. It is already populated, already occupied, by a family of objects whose orbits make the most extreme Kuiper Belt trajectories look conservative by comparison. The scattered disk does not sit neatly beyond the classical belt like a second ring placed concentrically outside the first. Its members are defined not by their current distance from the Sun, but by their orbital characteristics, specifically by the enormous range between their closest and farthest points. A scattered disk object at its closest approach may be only 30 to 35 astronomical units from the Sun, well within the inner boundary of the classical Kuiper Belt. At that point in its orbit, It is a near neighbor by outer solar system standards, but that same object, following its highly elliptical path outward, may travel to 200 astronomical units, 300 astronomical units, 500 astronomical units before gravity finally arrests its outward motion and begins pulling it back inward. The implication is that scattered disk objects spend only a brief fraction of their orbital periods anywhere near the classical belt. The rest of the time, the overwhelming majority of their centuries-long or millennia-long orbits, they are somewhere beyond 100 astronomical units, drifting through a region of space so remote that no current telescope has detected any object there through direct observation. They retreat into the darkness, spend decades or centuries or millennia at distances that dwarf anything in the classical belt, and then slowly fall back inward to make another brief pass through the inner boundary of their orbit near Neptune's realm. This means the scattered disk is not a place in the conventional geographic sense. It is a population of trajectories, a set of orbits that collectively define a region extending from the inner Kuiper Belt all the way out to several hundred astronomical units, occupied by objects that are almost never where you might expect them to be based on their average orbital distance. Detecting these objects is one of the most demanding challenges in observational astronomy. At 30 astronomical units, the inner edge of their orbits, where they are closest to the Sun and therefore brightest scattered disk objects, move relatively quickly against the background stars, making them somewhat easier to identify through the standard technique of comparing images taken on different nights and looking for objects that have shifted position. But the geometry of their detection is biased. Astronomers can only discover them when they are near perihelion, near their closest approach to the Sun, because that is the only time they are bright enough to detect. The vast majority of their orbits, the parts spent beyond 100 astronomical units, are completely invisible to current instruments. Finding them requires patience, measured not in hours, but in nights. A point of light that has moved slightly between images taken 2 or 3 nights apart, shifted by a fraction of a degree against a background of thousands of fixed stars. That is what a scattered disk object looks like in a telescope. The motion is slow, the object is faint, and the sky contains an enormous number of fixed points of light that could mask or complicate the detection. Automated software has improved the process substantially, but the fundamental difficulty remains. These objects are intrinsically faint. They move slowly, and the sky is very large. Between 50 astronomical units, where the classical belt fades, and approximately 2,000 astronomical units, where theoretical models suggest the inner Oort Cloud begins, there lies a zone that is essentially opaque to current science. Not empty? Almost certainly. But invisible. The objects that populate this intermediate region, if they exist in significant numbers, are too faint and too slow-moving to be detected by any telescope currently in operation or under construction. It is a blind spot of enormous proportions, a gap in human knowledge spanning nearly 2,000 astronomical units of solar system territory. How many objects do you think are hiding in that dark zone right now? Unknown to anyone? The honest answer is that no one knows, and the uncertainty is not small. Models of solar system formation predict that significant populations of icy bodies should exist in that intermediate zone, displaced outward from the original disk by Neptune's migration and by subsequent gravitational interactions. Some of those populations may be detectable by next-generation survey telescopes. Others may remain invisible for decades. The region from 50 astronomical units to 2,000 astronomical units is, at this moment, one of the largest unexplored territories in the solar system. Not unexplored in the sense that spacecraft have not reached it, but unexplored in the more fundamental sense that we cannot yet see it at all. In that blind zone, there is one object that breaks every explanatory model, and it may be the clue to a hidden planet. In 2003, astronomer Mike Brown and his colleagues at Palomar Observatory detected a faint slow-moving point of light in a part of the sky where no significant solar system object had been expected. It was designated 2003 VB12 and later given the name Sedna, after the Inuit goddess of the Arctic Sea. At the time of its discovery, it was approximately 90 astronomical units from the Sun, already well beyond the outer edge of the classical Kuiper Belt. But the distance at discovery was not what made Sedna remarkable. What made Sedna remarkable was its orbit. Sedna's closest approach to the Sun, its perihelion, the point where its elliptical path brings it nearest to the center of the solar system, is approximately 76 astronomical units. 76 astronomical units. That is the nearest Sedna ever gets to the Sun. Its entire orbit lies outside the classical Kuiper Belt's outer boundary of 50 astronomical units. Even at perihelion, it is 26 astronomical units beyond where the classical belt ends. At its farthest point from the Sun, its aphelion Sedna reaches approximately 937 astronomical units. And its orbital period, the time it takes to complete one full circuit around the Sun, is approximately 11,400 Earth years. 11,400 years. The last time Sedna was at the same point in its orbit that it occupies today, human civilization had not yet invented writing. The problem Sedna poses for planetary science is straightforward and has no clean solution. Neptune, the planet responsible for shaping the Kuiper Belt through its gravitational influence, orbits at 30 astronomical units. The classical Kuiper Belt objects and the scattered disk objects all show Neptune's fingerprints in their orbital histories, their resonances, their eccentricities. Their inclinations all trace back to gravitational interactions with Neptune at distances of 30 to 50 astronomical units. Neptune's gravitational reach is powerful but not unlimited. At 76 astronomical units, Sedna's closest approach. Neptune's influence is far too weak to have placed an object on the orbit Sedna occupies. The math does not work. Neptune cannot explain Sedna. Two explanations have been seriously proposed. The first involves the early solar system's stellar environment. The Sun did not form in isolation. Like most stars, it formed within a cluster of hundreds or thousands of other young stars, all born from the same collapsing molecular cloud. For the first few 100 million years of its existence, the Sun's neighborhood was crowded with stellar companions at relatively close distances, close enough that their gravity could have influenced the outer reaches of the solar disk. A passing star during that early period, approaching within a few thousand astronomical units of the Sun, could have gravitationally tugged on objects in the outer disk and pulled some of them onto extreme orbits like Sedna's perihelion distances, far enough from Neptune to be beyond its influence, but not so far that the Sun's gravity cannot still maintain a bound orbit over billions of years. The second explanation is closer and more immediate. Something large might still be out there. In 2016, Konstantin Batygin and Mike Brown published an analysis of 6 trans-Neptunian objects with extreme orbits, whose orbital parameters showed a statistically unusual clustering. The arguments of perihelion, the orbital angles describing where each object makes its closest approach to the Sun, were grouped together in a way that would be highly unlikely if the object's orbits were randomly distributed across the sky. The orbital planes were also tilted in similar directions. The probability of that clustering occurring by chance, Batygin and Brown calculated, was approximately 0.7%. Their proposed explanation was a 9th planet, a body with a mass somewhere between 5 and 10 times the mass of Earth, orbiting the Sun at a distance in the range of 400 to 800 astronomical units on a highly elliptical to significantly inclined orbit. Its orbital period would be somewhere between 10,000 and 20,000 Earth years. It would be so distant, so cold and so slow-moving that detecting it with current telescopes would require either extraordinary luck or a systematic all-sky survey deep enough to catch a point of light moving almost imperceptibly against the stellar background. the debate has not been resolved. Some planetary scientists find the orbital clustering compelling and consider a distant massive planet the most plausible explanation. Others argue that the clustering is an artifact of observational bias, the result of which parts of the sky surveys have covered most thoroughly, rather than a genuine physical signal. The sample of extreme trans-Neptunian objects is small enough that statistical flukes remain possible. Neither side has definitively proven its case. The Vera C. Rubin Observatory, designed to conduct the legacy survey of space and time. A 10-year systematic survey of the southern sky, reaching far deeper than any previous wide-field survey, is expected to dramatically expand the catalog of known extreme outer solar system objects within the coming years. If Planet 9 exists and its orbit carries it to a detectable distance within the survey area, Rubin has a realistic chance of finding it. If the survey completes its 10-year run and finds no evidence of a massive distant planet, that absence will itself be significant strong evidence that the clustering is indeed a statistical artifact rather than a gravitational signal. If a planet 5 to 10 times Earth's mass has been orbiting the Sun for billions of years at 400 to 800 astronomical units, completely unknown until now, what does that change about how we understand this solar system? It changes the boundary. It changes the inventory. It changes the question of what knowing the solar system even means. If an entire planet-sized world can hide in the darkness beyond the Kuiper Belt for the full span of recorded human history without anyone knowing it existed. But whether Planet 9 exists or not, what lies beyond is larger than any planet, a structure for which even the word enormous falls short. No one has ever seen the Oort Cloud. Not directly, not even close to directly. No telescope has resolved an individual object within it. No spacecraft has traveled anywhere near its inner boundary. No image exists of any part of it. By every conventional measure of scientific observation detection, imaging, measurement, confirmation, the Oort Cloud remains entirely invisible. And yet its existence is about as certain as anything in planetary science. The evidence comes not from the cloud itself, but from what it sends inward. Long-period comets' bodies with orbital periods of hundreds, thousands, or even millions of years, arriving in the inner solar system on orbits so elongated that their farthest points extend to enormous distances, have been observed and catalogued for centuries. What made astronomers eventually conclude that they share a common origin is not their composition or their brightness, or the spectacle they create when sunlight heats their surfaces and drives off gas and dust. It is their geometry. Long-period comets arrive from all directions, not preferentially from the plane of the ecliptic, where the planets orbit and where the Kuiper Belt is concentrated, not clustered in any particular region of sky. They come from above the ecliptic plane, from below it, from every point on the celestial sphere with roughly equal frequency. A population of objects that produces infalling comets from all directions in space must itself be distributed across all directions in space. It cannot be a disk. It cannot be a ring. It has to be a sphere, a vast, roughly symmetrical shell of icy bodies surrounding the solar system in every direction. Above, below, and all around, from which occasional members are dislodged by passing stars or the slow tidal pull of the Milky Way's gravity and sent falling inward toward the Sun. The Dutch astronomer John Oort formalized this reasoning in 1950, analyzing the orbital characteristics of long-period comets and concluding that they originated from a distant spherical reservoir at distances of tens of thousands of astronomical units. The structure has carried his name ever since. The estimated boundaries of the Oort Cloud place its inner edge at roughly 2,000 astronomical units from the Sun, 40 times the outer boundary of the classical Kuiper Belt, and its outer edge at approximately 100,000 astronomical units. 100,000 astronomical units. Each astronomical unit is 150 million kilometers. The arithmetic produces a number that standard scientific notation handles more comfortably than words do. But the words are 15 trillion kilometers to the outer edge of the Oort Cloud, expressed as a distance of approximately 1.6 light-years. 1.6 light-years. The nearest star to the Sun is Proxima Centauri, at a distance of 4.24 light-years. The outer boundary of the Oort Cloud extends approximately 38% of the distance to the nearest star, the Solar System, defined by the reach of the Sun's gravitational influence over a significant bound population of icy objects, extends more than a third of the way to the next star in the galaxy. That is not a solar system in the compact, poster-sized sense. That is an enormous gravitational territory, a sphere of influence that reaches deep into what most people would intuitively call interstellar space. The estimated population of the Oort Cloud is measured in trillions, perhaps several trillion individual icy bodies, comet nuclei, frozen mixtures of water ice, carbon monoxide, carbon dioxide, methane, and organic compounds, preserved in temperatures barely above absolute zero at distances where sunlight is so faint it provides essentially no warmth and almost no energy. Trillions of objects. It sounds denser than the Kuiper Belt. It is not. The volume of a sphere extending to 100,000 astronomical units is so incomprehensibly larger than the volume of the classical Kuiper Belt shell that distributing even trillions of objects through it produces a density far lower than anything in the belt. If the classical Kuiper Belt's volume were a single drop of water, the volume of the Oort Cloud would be an Olympic swimming pool. The trillions of Oort Cloud objects spread across that pool-sized volume are separated from each other by distances measured in billions of kilometers. A spacecraft flying through the Oort Cloud at any speed achievable by current or foreseeable technology would have essentially zero probability of coming within detecting range of any object. The cloud is there. Its contents are real. But they are so thinly scattered across so vast a volume that the cloud is, for any practical purpose of physical navigation, indistinguishable from empty space. What occasionally disturbs that near emptiness is gravity specifically. The gravity of passing stars and the tidal force exerted by the mass distribution of the Milky Way galaxy itself. These perturbations are weak at the scale of individual interactions, but operating over millions of years, they are sufficient to nudge Oort Cloud objects out of their stable distant orbits and set them falling inward along enormously elongated trajectories. The journey from the Oort Cloud to the inner solar system takes thousands or millions of years at the slow orbital speeds that prevail at such distances. But eventually, some of those objects arrive streaking through the inner solar system as long-period comets, briefly spectacular as sunlight volatilizes their surface ices and drives off the gas and dust that forms their glowing comas and tails. Comet Hale-Bopp, which appeared in Earth's sky in 1997 and became one of the most widely observed comets of the 20th century, is one of those visitors. Its orbital analysis places its origin in the Oort Cloud, the journey that brought it through the inner solar system in 1997, began millions of years ago, when some gravitational perturbation dislodged it from whatever stable distant orbit it had occupied since the early solar system. It spent millions of years falling inward before its brief passage through the planetary zone, the cosmic equivalent of a stone dropped from an enormous height, falling for an almost incomprehensible time before finally striking the surface. If the solar system extends 1.6 light-years in every direction, how far, actually, is the boundary between the solar system and interstellar space? The boundary is not sharp. It is not a wall or a line. It is a gradual fading of the sun's gravitational dominance against the combined gravitational environment of the galaxy. A transition zone rather than an edge, and one that shifts depending on how one defines the solar system in the first place. The question of where the solar system ends is, at those scales, not a question with a clean answer. The Kuiper Belt, the scattered disk, Sedna, the Oort Cloud, each layer larger than the one before. Emptier, more remote. But this is still not the largest thing. In 2004, the Hubble Space Telescope captured a direct image of something that, a decade earlier, would have been considered extraordinarily difficult to obtain. Around Fomalhaut, a young, bright star located approximately 25 light-years from Earth in the constellation Piscis Austrinus, Hubble resolved a distinct ring of material, a debris disk orbiting the star at a radius of approximately 133 astronomical units, broad and bright in reflected starlight, with a structure sharp enough to study in some detail. The image was striking not just because it existed, but because of what its structure implied. The inner edge of Fomalhaut's debris ring was remarkably sharp and well-defined, far more so than would be expected from a freely evolving disk of colliding particles gradually spreading under the influence of radiation pressure and mutual interactions. A sharp inner edge requires a confining force. Something is sweeping up material that drifts inward, maintaining the boundary through continuous gravitational clearing. The most natural explanation is a planet and unseen body orbiting just inside the ring's inner edge, acting on Fomalhaut's debris disk the same way Neptune acts on the Kuiper Belt, clearing its orbital neighborhood, maintaining the structure of the disk through ongoing gravitational interaction, leaving its signature in the geometry of the material surrounding it. The parallel to our own solar system is not subtle. Neptune defines the inner boundary of the Kuiper Belt by clearing material from its orbital zone. Something appears to define the inner boundary of Fomalhaut's disk by doing the same thing. The mechanism is identical. The scale is larger, 133 astronomical units compared to 30 astronomical units, but the physics is the same gravitational sculpting, operating around a different star. Beta Pictoris, approximately 63 light-years away, presents an even more detailed case. Its debris disk was first resolved in ground-based images in the 1980s and has been studied extensively in the decades since. The disk extends hundreds of astronomical units from the star in both directions, far larger in apparent extent than our Kuiper Belt, with a structure that shows warps, asymmetries, and gaps that astronomers attribute to the gravitational influence of planets embedded within or near the disk. At least 2 planets have been directly imaged in the Beta Pictoris system. Beta Pictoris b, confirmed in 2008, and Beta Pictoris c, confirmed in 2019, making it one of the very few planetary systems where both the debris disk and the planets shaping it have been directly observed. The connection between the planets and the disk structure is not inferred from indirect evidence. It is visible in the images. Then there is Epsilon Eridani, at approximately 10.5 light-years from Earth. It is one of the nearest stars to the Sun with a confirmed debris disk. The disk extends from roughly 35 to 90 astronomical units, a radial range that maps onto our own Kuiper Belt with an almost uncomfortable degree of similarity. The inner edge at 35 astronomical units corresponds approximately to the inner boundary of our classical belt. The outer extent at 90 astronomical units is broader than our classical region, but consistent with including scattered disk analogs. Clumps and concentrations within the disk suggest the gravitational influence of at least one planet sculpting its structure, in the same way Neptune shapes the orbital families of the Kuiper Belt. 3 stars, 3 debris disks, 3 independent examples of the same phenomenon, each one showing a ring or disk of icy and rocky material in the outer reaches of its planetary system, each one bearing evidence of planetary gravitational influence shaping its structure, each one in its basic architecture resembling what we observe beyond Neptune. This is not coincidence. It is process. The formation of a debris disk in the outer reaches of a planetary system is not a peculiarity of our solar system's particular history. It is the natural outcome of planet formation itself. When planets form from a protoplanetary disk, they incorporate most of the available material in the inner regions, where conditions favor accretion, and where the growing planets have enough mass to gravitationally dominate their neighborhoods. In the outer regions, where material is more spread out, where collision rates are lower, where orbital periods are longer, the accretion process is less efficient. Not everything gets swept up. The remnant material, the icy planetesimals that formed beyond the frost lines and were never incorporated into a planet, remains, sculpted and organized by the gravity of whatever planets did form, persisting as a debris disk for billions of years. If that process happens around our sun, it should happen around other stars with planets, and the observations confirm it. Debris disks have been detected around dozens of nearby stars using infrared telescopes, which can detect the faint heat emitted by disk material as it absorbs starlight. The systems that show debris disks are not unusual or exotic. They are ordinary planetary systems, similar to ours in their broad architecture, each with its own version of the frozen outer territory that we call the Kuiper Belt. Which means the Kuiper Belt is not a local feature. It is a universal one. Every planetary system that forms around a star like the Sun almost certainly produces a debris disk in its outer reaches, an enormous reservoir of icy, rocky material, organized by the gravity of whatever planets orbit closer in, preserving the original chemical inventory of the outer solar nebula in frozen form across billions of years. If every planetary system has a structure like the Kuiper Belt, how many unnamed frozen worlds is the universe hiding right now? The number is beyond any comfortable estimate. There are roughly 200 billion stars in the Milky Way galaxy alone. A significant fraction of them host planetary systems. If even a modest fraction of those systems produce Kuiper Belt analogs comparable in population to ours, hundreds of thousands of large objects, millions of medium ones, trillions of smaller bodies. The total number of frozen worlds orbiting in the outer reaches of planetary systems across the galaxy runs into numbers that human language was not built to handle. And here is when a simple question with no easy answer surfaces everything learned about the Kuiper Belt so far. All of it is only the surface. The current catalog of known Kuiper Belt objects numbers in the low thousands. A few thousand confirmed bodies, out of a population that models estimate contains hundreds of thousands of objects larger than 100 kilometers across, and millions more smaller than that. The fraction of the belt's true population that humanity has actually detected and cataloged is small, perhaps a few percent of the significant objects, and a negligible fraction of the total. The Kuiper Belt has been known to exist for just over 3 decades, and in that time, the tools available to study it have improved enormously. But the belt is large, its objects are faint, and the sky is vast. Progress has been real, but incremental. That is about to change. The Vera C. Rubin Observatory, built on Cerro Pachon in Chile, is entering full science operations. Its central instrument, a 3.2 gigapixel camera, the largest digital camera ever constructed for astronomical use, is designed to image the entire visible southern sky repeatedly over the course of a 10-year program called the Legacy Survey of Space and Time, or LSST. Every few nights, the survey returns to each patch of sky, building up a time-lapse record of the entire southern celestial hemisphere, deep enough to detect objects far fainter than any previous wide-field survey has reached. Moving objects, asteroids, Kuiper Belt bodies, scattered disk members, anything that shifts position against the background stars between successive visits will be identified automatically by software processing the incoming images in real time. The expected yield for the Kuiper Belt is transformative. Current estimates project that Rubin will discover more than 40,000 Kuiper Belt objects over the course of its survey. Not a modest increment over the existing catalog. a multiplication by an order of magnitude or more, from a few thousand known bodies to tens of thousands, spanning the full range of orbital families, distances, and sizes that the belt contains. What 40,000 objects makes possible is qualitatively different from what a few thousand allows. With a small sample, the orbital structure of the belt can be roughly sketched, the major populations identified, the resonances mapped in broad terms, the gross features of the cold and hot classical populations distinguished, with tens of thousands of objects distributed across all orbital families. The structure can be mapped in fine detail. Subtle concentrations and gaps become statistically significant rather than potentially coincidental. The boundaries between orbital populations sharpen. The fingerprints of Neptune's ancient migration become readable at a resolution that current data cannot support. And Planet 9, if it exists, becomes findable. Rubin's survey is deep enough and wide enough that a planet-sized body at 400 to 800 astronomical units, if it falls within the survey footprint at a detectably close point in its orbit, has a realistic chance of appearing in the data. If after 10 years of systematic sky coverage, the survey finds no candidate, that absence itself constitutes evidence, a constraint on where Planet 9 could be and how large it could be, strong enough to substantially reshape the debate. The question that has been open since 2016 may finally have a definitive answer, one way or the other, from the data Rubin accumulates. The observatory's discoveries will also inform the planning of future spacecraft missions. Every new Kuiper Belt object added to the catalog is a potential target, a world that has never been visited, whose surface has never been imaged at close range, whose composition has never been measured by an instrument close enough to matter. The targets most likely to receive dedicated spacecraft in the coming decades are the dwarf planets, Pluto, already visited by New Horizons, but never orbited; Eris, the most massive known scattered disk object, never approached by any spacecraft; Makemake and Haumea, both unvisited, both harboring unanswered questions about their compositions, their moons, and in Haumea's case, its extraordinary shape and ring system. Mission concepts for a Pluto orbiter have been studied seriously. The scientific case is strong. An orbiter would return data orders of magnitude richer than New Horizons' brief flyby, mapping the surface composition in detail, probing the interior with radar, monitoring the atmosphere over multiple Plutonian seasons as the dwarf planet moves along its elliptical orbit. The engineering challenge is real, but not insurmountable. The timeline is the hardest part. Even with advanced propulsion systems, a spacecraft sent to orbit Pluto would take somewhere between 15 and 20 years to arrive. The scientists who design the mission, who write the proposals and build the instruments and calibrate the cameras, will in many cases be retired or no longer working in the field by the time the spacecraft reaches its destination. The data will be analyzed by people who were children or not yet born when the mission launched. This is not unusual for deep outer solar system exploration. It is the norm. New Horizons was proposed in the 1990s, launched in 2006, and reached Pluto in 2015. The scientists who first advocated for it spent decades waiting. Every mission beyond the asteroid belt requires this kind of commitment, a willingness to invest effort and resources into something whose return will arrive in a future that the investor may not personally witness. Perhaps the most beautiful thing about space science is precisely this. It forces people to think beyond the span of their own lives. To design a mission to Eris, whose orbit takes it out to 97 astronomical units, whose closest approach to the Sun still puts it well beyond the classical Kuiper Belt, requires planning for a journey that would take decades. To send a spacecraft to Haumea and study its ring system up close. To see what Makemake's dark moon looks like from nearby. To orbit any of the mid-sized Kuiper Belt objects that New Horizons glimpsed only as faint specks in its long-range cameras. All of it requires institutional commitment, that spans career generations. The mission is designed by one generation of scientists, launched by another, and its data analyzed by a third. Meanwhile, New Horizons continues. Its nuclear power source, a radioisotope thermoelectric generator, decays at a known rate, producing less electrical power each year. Instruments have been selectively powered down to conserve energy for the most critical systems, but the spacecraft is still flying, still transmitting, still measuring the particle environment and dust density of the outer Kuiper Belt and the region just beyond it, sending data back across billions of kilometers to receivers on Earth. That's trained to detect the faint radio signal crossing that distance. Every day that New Horizons remains operational is another data point from a region no other spacecraft has entered. If you could choose one object in the Kuiper Belt to send a mission to any object, any world in that vast frozen wilderness, which one would it be? The answer reveals something about what matters most. The familiar complexity of Pluto, the extreme isolation of Eris, the geometric strangeness of Haumea, the pristine simplicity of an Arrokoth-like body untouched since the solar system's first days. Each choice is a different question about the outer solar system, a different thread to pull on in the attempt to understand how this place came to be and what it contains. But before this ends, there is one thing the entire journey has not yet said, and it is larger than everything that has come before. By this point, a new understanding has settled in. The solar system is not what the poster showed. It is vast far beyond Neptune, far beyond the classical Kuiper Belt, extending through the scattered disk and the mysterious intermediate zone and out to the Oort Cloud at 1.6 light-years. The Kuiper Belt is enormous. The Oort Cloud is the true outer boundary. The solar system is a layered structure, each layer larger and emptier than the one before it. And now, finally, after everything, the full picture seems clear. It is not clear. The picture just broke again. The Oort Cloud is not the boundary of the solar system. It is the boundary of the definition of the solar system, and those two things are not the same. A definition is a human construction, a line drawn in conceptual space to make a vast and continuous reality manageable to discuss. The actual gravitational situation at 100,000 astronomical units is something far more unstable, far more contingent, far more subject to disruption than the word boundary implies. At 100,000 astronomical units, the Sun's gravitational hold on an orbiting object is extraordinarily weak. The orbital velocities at those distances are vanishingly small, a few tens of meters per second, comparable to the speed of a running person. An object at the outer Oort Cloud is bound to the Sun by the most tenuous gravitational thread imaginable. And the galaxy is not quiet. Other stars move through the neighborhood of the Sun on timescales of millions of years. And when a star passes close enough within a light year or so, its gravity perturbs the outer Oort Cloud significantly. It tugs on those weakly bound objects, altering their orbits, sending some of them falling inward toward the Sun as long-period comets, and stripping others away from the solar system entirely, releasing them into interstellar space. This is not a hypothetical scenario. It has happened repeatedly throughout the solar system's 4.5 billion year history. Stellar flybys close enough to significantly disturb the outer Oort Cloud occur, by current estimates, roughly every few million years. Each one reshapes the outer boundary of the solar system not catastrophically, not all at once, but cumulatively, stripping away the most loosely bound objects, injecting a pulse of comets into the inner solar system, and restructuring the outer cloud in ways that persist for millions of years afterward. The Oort Cloud as it exists today is not the same structure that existed 100 million years ago. It has been partially stripped and partially reshaped by the stellar encounters that have occurred in the Sun's journey around the Milky Way. It will be partially stripped and reshaped again by encounters that have not yet occurred. Astronomers estimate that a star will pass within 1 light-year of the Sun approximately every few million years. At that distance, the gravitational perturbation to the outer Oort Cloud is sufficient to dislodge enormous numbers of objects from their stable distant orbits and send them falling inward. The result is a comet shower, a period of elevated long-period comet flux in the inner solar system, lasting hundreds of thousands of years, during which the rate of comet impacts on the planets is substantially higher than the background rate. The last major stellar encounter close enough to significantly perturb the Oort Cloud is not precisely known. What is known is that the current rate of long-period comet arrivals appears relatively low, consistent with an interstellar neighborhood that has been, for the past few million years, relatively undisturbed. The most recent known close stellar approach was the passage of a star called Schultz's star, which passed within approximately 0.8 light-years of the Sun approximately 70,000 years ago, well within the outer Oort Cloud's boundary, close enough to have disturbed it. What that means is the pulse of comets that Schultz's star sent falling inward is still in transit. Somewhere between the outer Oort Cloud and the inner solar system, a wave of dislodged icy bodies is slowly falling toward the Sun, taking millions of years to complete the journey. It has not arrived yet. It may arrive in the distant future as an elevated flux of long-period comets, a comet shower triggered by a stellar encounter that happened 70,000 years ago, before modern humans had left Africa. We may be living in the quiet interval between two storms. The Kuiper Belt is not the end. The Oort Cloud is not the end. Even the Sun's gravity is not a fixed boundary. It is something continuously renegotiated by the other stars in the galaxy, shifting and eroding and reforming over millions of years as the Sun moves through a neighborhood that is never truly still. The solar system is not a closed system, a gem in a protective shell, a bounded territory with defined edges. It is an open system, drifting through a galaxy of 400 billion stars that are all doing the same thing, moving, perturbing each other, exchanging members of their outer populations across the thin boundary between gravitationally bound and gravitationally free. Every star in the galaxy has its own Oort Cloud analog, and those clouds, at their outermost edges, may not be entirely distinct from each other. In the spaces between stars, the gravitational territories of neighboring stellar systems may overlap at their margins, blurring the line between one solar system's domain and the next. The poster on the classroom wall was not wrong because it compressed the distances. It was wrong because it drew an outline, and the solar system does not have one.